Okay, so let us start today's session. Good afternoon, everyone. Welcome to the third week of problem solving session for the deep learning course. As you know, I am Tanuka from ISC Bangalore. So in today's session, we will be talking about support vector machines or SVMs. So as you all know that SVM is a very commonly used classifier in the machine learning domain. So SVM is also a linear classifier. As we are talking about different classifiers, it is also basically a linear classifier. And what is the specialty of SVM? It is that you have, let's say, a two class classification problem. You have two sets of data points. Now when you go for designing the SVM classifier, that is, you want to determine the decision boundary, decision surface between the two classes that you will use for classification, then while computing that decision surface, you consider the margin between the two classes and you choose such a decision surface that maximizes the margin between the two classes. So by margin here, what we mean is, if you have, let's say, I have two sets of data points, one from class 1 and another set, let's say two more, and another set I have that is class 2. Now as you can see, of course, these data two classes are linearly separable, so you can have a decision surface somewhere in between the two classes. Now there can be a infinite number of such surfaces that you can put between the two classes, right? This can be this one, or you can have something like this, you can have something like this. Any of this is a decision surface between the two classes, which is correctly classifying all the training data. But in case of SVM, we do not choose any such arbitrary decision surface. What we do is, we choose such a surface that maximizes the margin between the two classes. So here this is the margin between the two classes, and I am placing the decision surface such that this margin is maximized. So this margin is basically this distance is basically the distance of the closest point of this class from the decision surface, and this is the distance of the closest point of this class from the decision surface. So both will be equal. You will put the decision surface midway. So when you increase, you maximize this margin, or in turn you are actually maximize the distance between the class and the decision surface, this and this you are maximizing, then the optimum solution that you get is this SVM classifier. Now so it's very clear that having larger margin will be helpful. For example, let's say if you have very small margin, let's say this is your decision boundary and only this much is your margin. Now when you go for classifying some unknown data point in real world scenario, there can be measurement errors as well, and here in the training data your closest data points were here from this side of the class. Now if there are some measurement error and some data point shifts slightly more towards the other class, it can get misclassified if you have a very small decision margin. But if you have a larger margin, you have more confidence. Even if there is small perturbation due to noise or something, even after that you will be able to classify. But yeah, even in that case also, if the perturbation is large enough, you can have misclassified examples, but the confidence increases when you have larger distance between the class and the decision boundary, or larger margin. So that is the idea of having a classifier which tries to maximize the margin between the two classes, and that is what SVM does. So let us today we will be solving problems around this SVM concept only. If you have any doubts at any point, you can just stop me, unmute yourself and speak up. So I'll start with a few problems. So the first one that I have is for a 2-class problem, what is the minimum possible number of support vectors? Assume there are more than 4 examples from each class. So can any of you give me the answer for this? If you have a 2-class problem, what should be the minimum possible number of support vectors? Neelam is saying 2. Yeah, of course it is 2. So Neelam, would you like to explain why you choose the answer 2? You are giving the answer as 2. You can just unmute yourself and tell us. Neelam? Okay, she is saying at least one vector from each class is required. Yeah, right. So when we are computing this margin, we have to compute the margin from some data point of each of the classes. So you need at least one point to compute that margin. And another way also is another point also is the support vectors are basically the closest points from each class to the decision surface. So any one point, at least one point will be the closest from each class. So at least 2 support vectors will be there if you have a 2-class problem. Now let's say these are the data points given. So here the red points belong to class 1 and the blue points belong to class 2. Now can you tell me which all will be the support vectors in this case? You can just put the xy coordinates. So first let us see which one will be the support vector for class 1 among the red data points. Anyone? Okay, Neelam said 4, 3. Anyone else?
Four and 3, which is the red one, and then for blue we could see 2, 2 over there. One is at 4, 5, and then other is at 7, 2.
Okay, so you are saying 1 from red class and 2 from the blue class. So these 2 and this one you are saying, right? Yeah, so both of you are correct only. So I'll explain in case anyone has any doubt. So here the decision boundary, this is one class and this is another class. So your decision boundary, the linearly separating decision boundary or decision surface should go somewhere in between the 2 classes. Now whatever point is nearest from each class to that decision surface, that is the support vector. So clearly from red class only this data point is closest to the decision surface. So this will be the support vector. This will be the support vector and its coordinate is 4, 3, as both Neelam and Lalita said. Now among the blue, So, the way I have drawn the decision for surface, both this point and this point looks to be the closest ones to that decision surface, but depending on what is the orientation of the decision surface for the maximum margin, either one or two or both can come up as the closest points or the support vectors. So, in case the decision surface is something like this, then you can see the red point is the same, but the blue point, this blue point is closest to the decision surface. But in this case you can see that the margin is very small in this particular setting. Again, if you have the decision surface like this, then only this point becomes closest to the decision surface, but again the margin is very small. Just a minute. Margin is very small. So, the optimum case where the margin is maximum will be the one that I drew earlier, like this, and in this case both of these points are kind of closest to this decision surface, and these point coordinates are 4, 5 and 7, 2 as Lalita mentioned. So, in this case we have 3 support vectors which are defining our decision surface, and these 3 support vectors are 4, 3, 4, 5 and 7, 2. Now, given this, the next question is, what is the equation of the decision surface using SVM? So as we know, the decision surface, as we drew, it will be a straight line passing between the 2 classes. Now, to compute that, what we'll do is, we will compute the equation of this boundary, which is the boundary for class 2. We will also compute this boundary, which is the boundary for class 1, and our decision surface will be midway between these two. So, first for the boundary of class 2, this is basically a straight line which passes through 4, 5 and 7, 2. So, simply we can use the formula of straight line, which is given as y minus y1 by x minus x1 equals to y1 minus y2 by x1 minus x2. We can simply use this formula and use x1 y1 as 4, 5 and x2 y2 as 7, 2 to determine the equation of the boundary for class 2. So, let us do that. So, this will be the boundary for class 2. Similarly, we can have a boundary for class 1 which passes through the support vector of class 1, which is this point 4, 3. Now, this will basically be a line parallel to this particular line, but passing through that red point. So, if it is parallel to this particular line, then simply the slope will be equal. If we write it in that form, y equal to mx plus c form, so the slope is minus 1. So, in this case, let us say the equation will be some y equal to minus x plus c, which will pass through 4, 3. If we simply put these values, which gives us that c is 7, and we already have the slope as minus 1. So, our final equation for this class 1 class 1 boundary is y equal to minus x plus 7, and the same for class 2 is y equal to minus x plus 9. So, our decision surface will be in between this, that surface will also be parallel to this. So, the slope will be the same, only the bias term will change because it is placed midway between these two. So, the equation of the decision surface will be y equals to minus x plus 8, which is midway between the two boundaries. So, this is our equation of the decision surface according to SV. I hope this is clear to everyone. If anyone have any doubt, you can post it in the chat, or you can unmute and ask at any point. I'll move on. You can stop me anytime. So, the next question is, we are considering the same setup. Now, we need to find the margin using SVM. So, margin can be computed in a variety of ways. The first way is we can use the formula that you have already known from the class lectures. So, can anyone tell me what is the formula for margin depending on the W weight vector? So, what if you are given the weight vector as W, what will be your margin? Okay, so you can go through the class lecture also once more, or I'll explain. So, the margin always is, okay, Mani is saying W transpose X plus C. Mani, that is not the margin. By margin I mean, so you have this boundary, you have this boundary, and you have this decision surface. What is this width? So, distance of the support vector of class 1 from the decision surface plus distance of the support vector of class 2. I mean, both will be equal. So, twice the distance of the support vector from the decision surface, that won't be W transpose X plus C. That is basically W transpose X plus C is basically used as the classification rule, as if W transpose X plus C is greater than 0, you put it in one class, it is less than 0, you put it in other class. But you can compute the margin from this rules, and if you do that, the margin will come as this 2 by norm of W. This is as given as the margin. So, I'll briefly do that derivation. So, let's say you have two sets of points, and this is your decision surface. So your W is somewhere in this direction, and this is this side's boundary, this is this side's boundary. Pardon me for the drawing, it's not actually symmetric. Maybe somewhere. Now let's say I call this point as x plus and this point as x minus. So I can have a vector joining x plus to x minus. That will be, or let's say I say the left side one is x minus, this is x plus. So I want the vector from x minus to x plus, that will be given by x plus minus x minus. This is the vector joining x minus to x plus. Now I need this width, and this is the direction of W, which is perpendicular to the decision surface. So if you simply take the projection of this vector joining x plus and x minus on the direction of W, you will simply get this, right? You will have to take the unit vector along W. If you take the unit vector along W and project your vector joining x minus to x plus towards that direction, you will simply get this part, right? So the unit vector along W will be W by norm of W, right? So to take the projection on this unit vector, what we need to do is we need to take the dot product between the two, inner product. So we can do this transpose this. This is our margin. Now you know that x minus is on this line. So x minus will satisfy W transpose x minus plus some B, which is the bias star, is equal to minus 1, and x plus will satisfy W transpose x plus plus B equal to 1, because that's how we designed the SVM classifier. We said that yi into W transpose x plus B always has to be greater than equal to 1. So on the boundary of each class, it will be equal to 1. So your W transpose x plus B will be 1 on one side and minus 1 on the other side. Let's take these two. So if I simply subtract, I will get W transpose x plus minus x minus equal to 2. So if we put that in this, we get 2 by norm of W. So your margin between the two classes is 2 by norm of W. Mani, I guess it's clear to you. If you have any doubts, you can put it up. Okay. So we can simply use this formula to compute the margin in this case. So here our decision surface is y equal to minus x plus 8, right? Y equals to minus x plus 8, or we can write it as x plus y minus 8 equal to 0. So what is our W in this case? W is 1 1. This is basically the coordinates of x and y, that is W, because this you can write in the form W transpose x plus c equal to 0. So W is your 1 1 vector. Now so the unit vector along this W direction, which is W by norm of W, will be, norm of W is 1 by 1 square plus 1 square, and you have 1 1. So it will be basically 1 by root 2 1 1. Now if you take any 2 points, any 2 support vectors, or no, you don't need to do that. So this is your okay, I'm sorry, I'll show it both ways. So one is just using this formula, which is 2 by norm of w, and w in this case is this vector 1 1. So norm of w will be 1 by root 2 as I computed here. So your margin will be 2 by norm of w, which is equals to, oh sorry, root 2. So 2 by root 2, which is equal to root 2. This will be your margin according to the formula 2 by norm of w. If you just take that formula as granted and put the value of norm of w into that, here w is 1 1, you get the margin as root 2. Also you can compute it the way I derived. So you have w by norm of w is this. Now if you just take 2 support vectors, let's say we take 4 3 and 4 5, 4 3 and 4 5 from the 2 classes. So this is our 4 3 and this is our 4 5. So the line, so the vector joining from 4 3 to 4 5, that vector is given by 0 2, which is basically 4 5 minus 4 3. This is 0 2. Now if we simply project this vector along the unit vector along w, we will get the margin. So how do we do that? As I computed before, it is this into x plus minus x minus. So w by norm of w, you have 1 by root 2 1 1. I'll do that, I did the transpose, so it's now a row, and x plus minus x minus in this case is 0 2. So if you simply do that dot product, it will become 2 2, which is equal to root 2. So like that also you can get the same margin. Both ways you are getting the same margin. Another way is also possible for solving this margin, computing this margin, which is, so you have this decision surface, you have 2 support vectors from this class, you have 1 support vector from this class. You can simply compute this distance or this distance, and twice of that distance is your margin, right? So this is the x plus y minus 8, right? This is the equation of your decision surface. Now if you have any surface given by ax plus by plus c equals to 0, and you want to compute the distance of a perpendicular distance of a point x naught y naught from that particular surface, so all of us know the formula. The distance will be given by ax naught plus by naught plus c by root over a square plus b square right. This is the expression for distance of x naught y naught from the surface given by ax plus by plus c equal to 0. This is a standard formula. Now here you need the distance of the point. Let's say we take this one. Let's say we take this particular point. This particular point in our case was 4 3. So we have to compute the distance of 4 3 from the decision boundary x plus y minus 8 equal to 0. So what will be the value? x is 4, y is 3 minus 8 divided by root over, here your x and y both has the coefficients as 1, so both a b are 1, so a square plus 1 square plus 1 square, and you basically take the mod of this, right? Yeah, minus 1 by root 2 mod, which becomes as 1 by root 2. So this is the distance of the point 43 from the decision surface. So your margin will be simply twice of this, so margin will be 2 times of this, which is root 2. So like that you can compute the margin in different ways. These are 3 different interpretations of how you can do the margin computation. If you can simply use the formula of 2 by norm of w, you can compute the w vector, take the norm of that and put in that formula, or you can, if you don't remember the formula, you can simply compute the distance of the support vector from the decision surface, and twice of that will give you the margin. Also you can take the vector joining one support vector from each class and project it along the unit vector in the direction of w, that will also give you the same margin. So all of these are different ways of approaching the same margin computation problem. Okay. Now let us move on to the next question. So now we have the question as classify the unknown point 5.23 using SVM. So our decision surface, as we saw, is x plus y minus 8 equal to 0. Now first we should determine which side is the positive side and which side is the negative side. So if we take class 1, one example, let's say we take this point only 4, 3. If you put that, you see 4 plus 3 minus 8, so 7 minus 8, it is minus 1, that is less than 0. So if this is the decision boundary, this side is less than 0 and this side will be greater than 0. Now when you have an unknown point, you have to put it in the equation of the decision surface, that is x plus y minus 8. You put your unknown point values in that and you see whether it is positive or negative. If it is positive, then in this case it belongs to class 2, and if it is negative, it belongs to class 1. So based on this idea, can someone tell me in which class we should put 5.23? So Neelam is saying class 2. Any other answer, or everyone is agreeing it's class 2?
Class 2, ma'am, as it is coming point 2.
Okay. So it is 5.2 plus 3 minus 8. So it's coming as 0.2, correct, which is greater than 0. So this point 5.23 is an element of class 2. Correct. Now you have the complete, we solved the complete pipeline. We saw which are the support vectors, what is the decision surface, what is the margin, how do you classify a new point. Now let us see this question. Will the decision surface using SVM change if one more data point from class 2 is at 6, 6? So 6, 6 is this point. Here you have one more blue point. So do you think adding this point in the training data set will change the decision surface? Okay, Neelam said no. I'm getting answers from only Neelam. Anyone else wants to volunteer?
No, ma'am, as it is coming in class 2 only.
Okay, what is the reason you are saying?
It is coming in class 2.
Yeah, it's that's the given to you. Okay, it's from class 2. Yeah, Neelam, your reason is correct, as the new point is not a support vector. So this new point that you have at 6 that is much within the class, it is not at all towards the class boundary, and your decision surface only depends on the support vectors, which are the points on the class boundary. So adding one point inside the class, anywhere inside you add, that doesn't affect your decision surface computation. So since we are adding it much inside the class, it will not affect. So your decision surface will remain the same. But if we add the same point, instead of at 6, we add it at 6, so we add it at this place. Let's say this is the case. Then I guess everyone will agree that now the decision surface will be changed, because earlier your class boundary was through this. Now you have one more data point and your class boundary has now become this. So now you have your support vectors have changed. This and this has become your support vector from class 2. This is no longer your support vector. So once your support vectors have changed, your decision surface will also change. So in this case, your decision surface will change. I hope this is clear to everyone. I'll take 2 minutes gap. If anyone have any doubt, you can put it up. Then I'll continue. So now we have one more similar type of problem. So here it's given that suppose we have
Excuse me, ma'am.
is someone saying anything?
Ma'am,
Yeah.
in the previous question, if due to some error, one of the points is added in another class. For example, a class 2 point is added in class 1 due to some error, then what will happen in the decision surface?
Uh, so okay, so this here we are adding the points in the training data set. So you already know whether it is class 1 or class 2. So based on this training data, you decide whether where should be the decision surface. So in, for example, let's say your new data point comes somewhere here, or you want it to, okay, I guess, let's say it comes somewhere here, that's what you are mentioning, right?
Yes.
Yeah. So in this case, we cannot completely correctly classify all the training data points with any of the decision surfaces. So there is something called soft SVM. So there we put a penalty term and we try to minimize that penalty. So if you are misclassifying any of the training data points using your decision surface, you get a penalty for that. You can add, along with maximizing the margin. Here margin you will compute with the same data points. Along with that, you add one more term in your objective function, that there is a penalty if some data points get misclassified due to this particular decision surface, and you try to minimize both of these. Then you will have a compromised decision surface that will again come somewhere here only, and this particular training data point will not be correctly classified with that. So this is called soft SVM. You can look into that.
Thank you.
So this is in practical scenario that will always happen, that you won't be able to completely separate the two classes with any decision boundaries. Not one, you will have multiple points which are being misclassified wherever you put the decision boundary. In that case, you just consider both of the things. You try to maximize the margin with whatever decision boundary you have, as well as you try to minimize the penalty of misclassifying with that decision surface. Now this one. So here we have a 1D feature x, which is a real number, and the class label is binary. So you have two classes, 1 or -1, and there are 3 points in your data set, -1, 1 and 3. -1 belongs to the class -1, which is this P1 point. 1 belongs to class 1, 3 also belongs to class 1. Then which of the following is true with respect to SVM? So maximum margin will increase if you remove the point P2 from the training set. It will increase if you remove the point P3, or it will remain same if you remove the point P2, or none of the above. What will be the correct answer according to you? Anyone? Neelam is saying A. Okay, so let us see this. So let's say this is the real number line. So your P1 point is here, -1. This belongs to class -1. I'll put it as a cross. Then P2 is at 1. Let's say this is 0. Your P2 point is at 1. This is belonging to class 1. And P3 point is at 3. This is also belonging to class 1. Now if you put the decision boundary, you can see both these are belonging to the same class, this and this. So you will put the decision boundary here, which is midway between these 2 points. You'll put your decision boundary here. That will give you a perfect separation with the maximum margin, right? So in this case, both this one and this one will become your support vectors. So P1 and P2 are your support vectors. So as we already saw that in case you change your support vector, you remove your support vector or you add a new data point which now becomes your support vector, your decision surface changes. Now if you remove this point P2, if you remove this one, so now this point 3 is becoming your new support vector. So your decision surface will be shifted and it will be somewhere here, and you have a larger margin in this case. So if you remove P2 in this case, your maximum margin will increase. Whereas if you remove P3 and if you would have kept P2 as it is, nothing will happen to your decision surface because P3 is not a support vector. But once you do some modification with P2, your decision surface will change as well as your margin will also change. So here, option A is the correct answer. Okay. Now let us see this one. Let's say if we employ SVM to realize 2 input logic gates, then which of the following will be true? The weight vector, here by weight vector we mean the weight vector along with the bias term is augmented. So the augmented weight vector we are thinking about. That for AND gate and OR gate will be same, or the margin for AND gate and OR gate will be same, or both will be same, or none of the two things will be same. What is the case? Now to do that, let's first see the point distribution in case of AND and OR. It's a 2 input logic gates, so the inputs be x1 and x2. So in case of AND, your 0 point, 1 point and 1 point, all these three will lead to the output of 0. So all these 3 belongs to one class, and when you have both inputs as 1 1, you will have the output as 1. So this data point belongs to the other class. So these are the two classes in case of AND gate. Now in case of OR gate, 0 0 is in your 0 class, 1 0 0 1 1 1 both gives the OR output as 1. So these 3 is in your other class, which is the class 1. This is in case of OR. So now these are the, in two cases, these are the two sets of data points. So first let's say we take the AND case. So if we want to draw the decision surface, that will pass somewhere through here, and this is your boundary of this class, this is your boundary for this class, and this is your margin. And when you go for OR, your decision surface passes somewhere here, and these are the boundaries. So this is your margin. So you can easily see that the weight vector along with the augmented weight vector is not different. It's different. So the orientation of the decision surface is same in both cases, that is the orientation at which the decision surface is placed, that's the same, but the absolute position is different. It's in case of AND, the decision surface is towards more right than the OR case, so the bias term is different in the two cases. So when you have the augmented weight vector, that will be different in the two cases. But if you see the margin, so in both cases, as you can see that the margin will be the same, because this distances are same, and this line is in both cases midway between the boundary of the two surfaces. So in both cases this arrangement is kind of similar, though it is shifted in the absolute position, but the arrangement is similar. So you have the margin equal in both the cases. You can simply compute the margin also and see it. So for example, if we want to do that, so this is our decision surface, right? So our weight vector will be perpendicular to this. So in this case, it is basically our weight vector is at 45-degree angle with the x1 axis, right? That will give us the optimum decision surface. So if that is the case, then our weight vector will be given by 1 1, w will be given by 1 1, since it is at the 45-degree angle. So if we want the unit vector along this direction, that will again be 1 by root 2 1 1. So if we simply take 1 by norm of w, we will get the margin, and the margin will be 2 by norm of w root 2, it is root 2, right? In case of the OR gate also, the orientation of the decision surface is the same. So your weight vector w will again be the same 1 1 vector, and if you take 2 by norm of w, you will get the same margin as root 2. So in both cases your margin is the same, but your weight vector along with the bias term augmented is not the same. So option B is your correct answer. The margin for AND gate and OR gate will be the same. Now we saw the we saw the margin computation, the decision boundaries, how to classify new points and all. Now let us see the training aspect of this SVM classifier. So during SVM class, during obtaining the decision surface of the SVM, what is our main intention? This is, we want to maximize the margin between the two classes, and our loss function is basically based on that idea. So using that concept, the question says, what is the shape of the loss landscape during optimization of SVM? Is it linear, is it paraboloid, ellipsoidal, or non-convex? Mani is saying it's paraboloid, and that's absolutely correct. So in SVM, what, as I said, the idea is to maximize the margin, and as we have seen quite a few times, that your margin is given by 2 by norm of W. So you needs to maximize this margin, or you can say you need to minimize this thing. 2 by norm of W you need to maximize, so inverse of that you need to minimize, or to make it a convex problem, we take the square of it. So we will have to minimize norm of W square divided by 2 in this case. So this you can write as W transpose W. So this is a, as you can see, quadratic optimization problem, and since this is a quadratic optimization problem of this form, half of W transpose W, it will have the shape of a paraboloid. For example, if it's a 1D case, it's W square, if W is 1D, so that will give you, if you plot W square by W, you will get a function like this, which is kind of a parabola shape. So whatever is the dimension of the problem, your loss landscape for optimization will always be in the shape of paraboloid. Now if that is the case, can someone tell me how many local minimum will be encountered while solving the optimization for maximizing margin for SVM? Anyone else? Okay, yeah, both of Abhinash is saying infinite. Okay, Abhinash, can you speak up and tell us why do you think it's infinite?
Ma'am,
Yes.
there can be one global minimum, but there can be a number of local minimum. That's why.
So the shape that we already discussed, the shape of the function is like this only. You have a paraboloid shape. It's a complete convex function. So if you, it's in one dimension, it's a parabola. There is just one minima to it. It's just this one. There is this, yeah, what you were saying is correct. In case of a convex problem, you in a case of optimization problem, you can have one global minimum and infinite number of local minima, but given this particular shape for the loss function of SVM particularly, which is a paraboloid shape, here you cannot have infinite number of local minima, because this particular graph, as you can see, it has just only one minimum. If you extend it to higher dimension also, this remains the same. You have only one minima to this function. So it's a convex function. Is that clear to you, Avinash?
Yes, ma'am.
Okay. So the answer here is correctly given by Mani and Lalita. There will be only one local minimum, since this is a paraboloid. Now the last question that I have is, the values for Lagrange multipliers corresponding to the support vectors can be less than 0, greater than 0, any real number or any non-zero number. So this is the Lagrange multiplier that we use while forming the loss function for SVM optimization. So basically we have to minimize this thing that we already mentioned, that is maximize the margin, subject to the constraint that yi into W transpose xi plus b should be greater than equal to 1, right? for all I. So we simply put that in a Lagrange multiplier form. So this becomes our loss function. Right, I equals to 1 to n. So here this alpha I is your Lagrange multiplier. So for each sample, each data point, ith data point, your Lagrange multiplier is alpha I. Now if you just consider the support vectors, only those data points. So in that case, what will be the values of the Lagrange multipliers? Is it less than 0 or greater than 0 or any real number or any non-zero number? What do you think, guys? Neelam is saying greater than 0. Anyone else? Mani is also saying greater than 0. Yeah, both of you are correct. So what we know is that our decision surface, the weight vector W, basically depends on our support vectors, right? So our W star, if we say the optimum weight vector, then that is given by alpha I, yi, xi, and this is basically only the support vectors are contributing to this. So the support vectors must have the alpha i's non-zero, I mean positive. So in that case only it will contribute to this. Now we can derive this from the optimization point. So the optimization function that we had is this. Right? This was the optimization problem. So this is a constrained optimization problem, which is a loss function is a function of all these things, W, B and alpha. With respect to all three of these, you need to minimize this loss function. So this is a constrained optimization problem. So if you want to solve this, we generally use the Kuhan-Tucker conditions, the KKT conditions. So if we apply the KKT conditions, if you know, you will be able to relate. Otherwise you can just take the conditions for granted for now. You can just look into the KKT conditions for constrained optimization later. So the conditions that we will have for solving this optimization problem, first one will be gradient of L with respect to W will be equal to 0. So these are the standard KKT conditions I am putting for this non inequality type of constraint. So if you have this gives you W equals to summation I equals to 1 to n alpha I yi xi. Second condition is del L del B equals to 0. That gives you, so you will have to consider only this term, this one, so which is summation of alpha I yi b, negative of that. So the derivative that you will get is alpha I yi when you are differentiating it with respect to b, and summation of that over I equal to 1 to n, that should be equal to 0. Actually you will get a negative of this, but since it's equal to 0, so I am not mentioning the negative sign. So this is the second condition. Along with that, the constraint that you have, that is one other condition among the different KKT conditions. So This is one more condition. Another two are all the alpha i's should be greater than equal to 0, and last one is alpha I into 1 minus yi w transpose xi plus b should be equal to 0 for all I. These are the standard KKD conditions for solving any constraint optimization. Now if you consider these two, so your alpha i's can be 0 or positive, negative values are not possible. So if you consider those particular points, let's say we form a set S where only those x's belong, xi's for which alpha I is greater than 0. If you consider only those points, for them, if you look into this last condition, for them alpha I is positive or greater than 0, and the product of these two terms is 0. So essentially this particular term 1 minus yi into w transpose xi plus b will be equal to 0 for this point, for any of the points belonging to S. So if x I is element of S, then 1 minus yi into w transpose xi plus b will be equal to 0, or your yi into w transpose xi plus b will be equal to 1. So when does that happen? It is equal to 1 at the boundaries. So these are basically the support vector points. So for those points we can see that you will have alpha I greater than 0, and if you put that in your final this w condition, you have alpha I yi xi for all I. Now whatever alpha I are 0, those doesn't contribute, so you will have only those for which alpha I is positive, that is only for xi element of S. Xi element of S. So your W is only a linear combination of your support vectors, and the alpha i's corresponding to these support vectors are positive. So if from here we took the positive ones, the for which alpha I greater than 0, we put it in this constraint. What we see is if alpha I is 0, then this remaining term 1 minus yi into w transpose xi plus b, that should be equal to 0. That means those points are on the boundaries of the two classes. So whatever points have alpha I greater than 0, those will come on the boundaries of the two classes. So those will actually be the support vectors. So we can say that for support vectors alpha I will always be greater than 0. Greater than 0. Yeah. Okay, so these were the problems planned to be solved for today. If you have any doubts from any part, you can ask. This session will be live, as you know, till 6 p.m. I will be available till that point. If you have no doubts, you can leave the meeting now itself. I will not solve any other problems from my side, but if you put up any question, I am here to solve that. Guys, whoever is joining now, so this session was from 4, so I have already solved today's whatever problems I planned for, and this I am online till 6. If you have any doubts, today we were discussing SVM to give you the brief. If you have any doubts, you can ask me. Otherwise, the problems that I have solved, that you can look in the video recording. Any doubts regarding SVM or previous sessions doubts also, you can ask it. The video recording will directly not be available on NPTEL portal. They actually put up a Excel sheet for the problem solving sessions. You will get the video recording as well as the slide link in that Excel sheet. You can go there and watch it out. It's actually hosted in YouTube. So it will not be available directly after this. So maybe tomorrow or day after you will get this recording. I am not sure about that which IIT will conduct exam. Not at all sure. Hello Chinmay. So in today's session we have discussed about SVM. So the session was from 4. So whatever problems I have planned, I have already solved it. If you have any doubts, you can ask me at this point. If you want to look at the problems that I solved, you can look in the recorded session. But any doubts if you have, I'll be happy to solve that.